In this lesson, we're going to cover optimization. The steps for solving optimization problems: number 1, draw a diagram and identify all the knowns and unknowns. Number 2, write an equation for the quantity that is to be maximized or minimized. Number 3, express the equation in terms of only one variable. And number 4, find the maximum or minimum values by checking the critical numbers of the function. This example says a long rectangular sheet of metal, 12 inches wide, is to be made into a rain gutter by turning up two sides so that they are parallel to the sheet. How many inches should be turned up to maximize the capacity of the gutter, and what is that maximum capacity? So I drew the rectangular sheet of metal right here. You can see it's 12 inches wide, and then the length, I just labeled it generic L. I put dotted lines right here and here to indicate that those were the two sides that you're going to turn up, and then you can see the diagram down here. And then I labeled this length X, so that means this height is going to be X right here, and then this is the length. If this whole side is 12, and then you take away these two x's, that means from here to here is going to be 12 minus 2x. So now you can see the shape of the gutter with its dimensions. The question is asking how many inches should be turned up, so we're solving for x. I just made a note that L is a constant, and because it says that we're trying to maximize the capacity, so I wrote we're maximizing the volume of the gutter. In this box, we're writing the equation of what we're trying to maximize. So since we're maximizing volume, that's going to be x times 12 minus 2x times L. So I wrote V of x is x times L times the quantity 12 minus 2x. So I'm going to multiply these together and distribute them to the 12 and the minus 2x. So we get 12Lx minus 2Lx squared. And remember, to find a maximum, we're going to take the derivative of this and then find the critical values. And remember, L is a constant, so it's just 12L, and then when you're taking the derivative of 12Lx, the derivative is just going to be 12L. Again, over here you have negative 2L, that's the constant in front of the x squared. So when we take the derivative, we're going to bring this 2 and multiply it to the front, and then subtract 1 from the exponent to just get x to the 1, or just x. For critical numbers, this derivative doesn't have any values for which it doesn't exist, so next we just check where it's equal to 0. To solve for x, we're going to divide both sides by 4L, and we get the critical number x equals 3. So down here, we're going to verify whether at the critical number x equals 3, that v has a max or a min. So we're going to test values around 3, and remember, when we test values around 3, we're plugging them into v prime. So when we plug 2 into v prime, we're going to plug it in right here. So you get 12L minus 8L is going to be positive 4L. When we plug in 4, we get 12L minus 16L, so that's negative 4L. And I wrote it out, since v prime changes from positive to negative at x equals 3, v of x has a relative maximum at x equals 3. And the problem also asks, what is the maximum capacity? So we're going to take the value 3 and we're going to plug it into the volume formula. All right, so the gutter should be turned up 3 inches, and the maximum capacity is 18 times the length, inches cubed. This example says a farmer has 2,400 feet of fencing, and he wants to fence off a rectangular area that borders a straight river. He needs no fence along the river. What are the dimensions of the field which produce the largest area, and what is that maximum area? So we're going to label this length x and this length y. So we're trying to solve for x and y and then maximize this area. So over here, we want to set up an equation for what we're trying to maximize. So I have area equals x times y, and we want this to be with respect to only one variable. So we're going to use the other piece of information that's given, and that's 2,400 feet of fencing to fence off this area. So we have 2x and 1y equals a total of 2,400. So we're going to write that in this bottom left box. For future problems, just make sure you're paying attention to how many x's and how many y's, because again, different problems will have different scenarios. So there might be like 5 x's and 2 y's or some other variation. So make sure you're setting that up correctly, and then you're setting it equal to the total amount of material. So we're going to solve for y. Once we isolate y, we can take all of this and plug it back in up here. Before we take the derivative, I want to distribute this x. So now we have a with respect to x. We have negative 2x squared plus 2,400x, and now we can take the derivative. To find the critical values, there's no values that will make this undefined, so we're just going to set it equal to 0 and solve, and we end up getting 600 as our critical value. So now we go to this bottom box, we label 600 as the critical number, we're going to label this a prime of x, and we're going to test values around 600. So I plugged 500 and 700 into a prime of x, and you get positive 400 and negative 400. So this is positive, this is negative, and you can see A prime changes from positive to negative at 600. And I wrote it out, since A prime changes from positive to negative at x equals 600, A of x has a maximum at x equals 600 feet. Since the problem wants us to find x and y, we already have x, we're going to plug x back in here to solve for y. And then finally, the problem wants us to identify the maximum area, so we'll take those two values and multiply them together, or we can take the x value and plug it into our area function here. Either way works. So when you plug in 600 right here, you get y equals 1200 feet. So our dimension is going to be 600 by 1200, and then the maximum area that's produced is going to be 720,000 feet. So we get 600 feet by 1200 feet produces the largest area of 720,000 feet squared. For this example, it says an open box with a rectangular base is to be made from a rectangular piece of cardboard, which is 16 inches wide and 21 inches long, by cutting a square from each corner and then bending up the rectangular sides. Find the size of the corners that will maximize the volume of the box. So I drew a rectangular piece of cardboard. The length is 21 inches and the width is 16 inches. And then we're going to cut out little squares from each corner, and the square has length of x. And I drew it where the corners have been cut out, and then you construct it into a box right here. So the box will have height x. And then if this x and this x are both being cut out of this full length of 16, that means this is going to be 16 minus 2x. Similarly, this will be 21 minus 2x. Finally, we're solving for x, and we're trying to maximize the volume. So again, whatever you're trying to minimize or maximize, that's the equation that you put over here. So we're going to set up the volume of this box. So we have volume equals x times the quantity 16 minus 2x times the quantity 21 minus 2x. And I'm going to FOIL these out first. I'm going to combine like terms. The negative 32x and the minus 42x is going to be negative 74x. And at the same time, I'm going to distribute this x. All right, we're ready to take the derivative. And again, when finding critical numbers, there's no values that makes this undefined, so we're just going to set it equal to 0 and solve. I'm going to factor out a 4 from every term, and I'm going to divide both sides by 4. At this point, this trinomial actually factors, and it factors to 3x minus 28 times x minus 3. So we get critical numbers 28 over 3 and positive 3. All right, so we're putting our critical numbers on the number line for v prime, and we're going to test values around them. And again, we plug 2 into v prime, then we plug 4 into v prime, and then finally 10 into v prime. We get a positive number, then we get a negative number, then a positive number. And again, we're trying to maximize the volume, so right here at 3, v prime changes from a positive to negative, indicating that the volume has a relative max there. And again, over here, v prime changes from a negative to positive, so that would indicate a minimum at 9 1/3. So since v prime changes from positive to negative at x equals 3 inches, v of x has a maximum at x equals 3 inches. This example says find the maximum volume of a cylinder inscribed in a right cone with a height of 12 inches and a radius of 4 inches. So you can see I drew the right cone. It has a height of 12 inches and a radius of 4 inches. And then we have a cylinder inscribed inside of the cone. The base of the cylinder lies on the base of the cone, and you can see the height of the cylinder comes up to the cone. And we're trying to maximize the volume of the cylinder. So that's the formula we're going to write over here. So for the volume of a cylinder, we have the area of the base, which is pi r squared, and then we times that by the height of the cylinder, which is h. So right now our volume is with respect to r and h, the radius and the height, but we want this to be with respect to only one variable. So we're going to use some information with this original picture. So if we look at this part of the cone, you have again radius is 4, the total height is 12, and then right here you have the radius of the cylinder, and then from here to here is h. So I drew that diagram down here. You have the radius is 4, the height is 12, and then you have this radius of the cylinder and its height is h. So if this whole length is 12 and this is h, then we would say that this is 12 minus h. We have similar triangles, so we have this guy and then this big one. So right here is r, and then this side is 12 minus h. For the big triangle, we have 4, and this whole side is 12. So that's what we're going to set up in a proportion. So I have r is to 4 as 12 minus h is to 12. So next we're going to cross multiply, and finally I want to solve for h. So we end up getting that h is equal to 12 minus 3r, so we're going to take that and substitute it into the equation up here. So now we have the volume of the cylinder with respect to just one variable r. So before we take the derivative, we're going to distribute. So we have v equals 12 pi r squared minus 3 pi r cubed. So here's the derivative for v, so now we're going to find our critical numbers. And at this point, we're going to set both of these equal to 0. So now we have a product equaling 0, so we can set them both equal to 0 and solve. So we end up getting 0 and 8/3 as our critical numbers. Since these values represent a radius on a cylinder, we're going to cross this option out because we can't have a 0 radius if we're going to have an actual cylinder. So now we're going to test 8/3 on our number line. All right, so we have 8/3 or 2 2/3, and we're going to test values around and plug them into v prime. Okay, so when we plugged in 2, we get positive 12 pi, so that's going to be a positive. And then when we plugged in 3, we get negative 9 pi, so that's negative. So you can see that v prime at 8/3 changes from positive to negative, therefore v has a relative maximum. So since v prime of r changes from positive to negative at r equals 8/3, v has a maximum at r equals 8/3. And the problem wants us to maximize the volume of the cylinder, so we're going to take our 8/3 and we're going to plug it into our volume right here with respect to r. So our maximum volume is going to be 256 over 9 pi inches cubed. This example says a circular cylindrical metal container open at the top is to have a capacity of 24 pi cubic inches. The cost of material used for the bottom of the container is 15 cents per square inch, and the material used for the lateral surface is 5 cents per square inch. If there is no wasted material, find the dimensions that will minimize the cost of making the cylinder. So the volume of our cylinder is supposed to be 24 pi cubic inches, and then we have the cost of the material, the base is 15 cents, cost of the lateral material is 5 cents per square inch, and we're trying to minimize the cost of the container. Also, it says the container has an open top, so when we're talking about the container, we have the base, which is a circle, and then we have the lateral surface area, which if you open it up like a soup can label, it's going to be a rectangle. So first we're going to look at the base, and that material costs 15 cents per square inch. So the area of the base is pi r squared, and then we're timesing that by 0.15. So again, the lateral area is a rectangle, the length is 2 pi r, the circumference of the circle, and the height of the rectangle is just the height of the cylinder, which is h. And then we're timesing this by the cost of the lateral material, which is 0.05. Before we take the derivative, we want only one variable. Right now we have r and h, so we're going to use this piece of information. It says the volume is 24 pi. So we're going to go down here and we're going to write volume of a cylinder is the area of the base times the height, and we're setting that equal to 24 pi. So now we have an equation. I'm going to divide both sides by pi, and I'm going to solve for h. So we get h is equal to 24 over r squared, and that's what we're going to take and plug in right here. So I rewrote this as 0.15 pi r squared. Then I multiplied the 2 and the 0.05 and got 0.10, dropped down the pi, dropped down the r, and then instead of h, I wrote 24 over r squared. Finally, we multiply 24 by 0.1 and you get 2.4, and then r divided by r squared is the same as r to the negative 1. So now we're ready to take the derivative. So we get 0.3 pi r minus 2.4 pi r to the negative 2. I moved this r to the negative 2 to the denominator, so now we have this expression. We can check where this doesn't exist. It doesn't exist at r equals 0, but because that represents an actual radius of a cylinder, we're not going to use r equals 0 as a critical number. So we're just going to set this equal to 0 and solve. At this point, it's a proportion, so we'll cross multiply. So I'm going to bring this r squared up to the left, making r cubed, and then I'm going to divide both sides by 0.3 pi. So r cubed is equal to 2.4 pi divided by 0.3 pi. The pi's cancel, and we get r cubed equals 8. So we end up getting that r equals 2 for the critical number. So we're going to put 2 on our number line and label it c prime of r, and we're going to check values around 2. So we're going to plug in 1 and 3 into the derivative of c, and I'm just going to use a calculator. And I wrote it out. Since c prime of r changes from negative to positive at r equals 2, c of r has a minimum at r equals 2 inches. And the original problem wants us to find the dimensions that will minimize the cost of making the cylinder. So we're trying to find r and h. So we already have r. We're going to take r and plug it in here to solve for h. So I wrote it out. When r equals 2 inches and h is equal to 6 inches, the cost of making the cylinder will be minimized. Alright guys, thanks for watching!